Hello, everyone, and welcome back to another exciting York Observatory TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Dr. Elena Hyde, and I'm very, very pleased to announce we have an absolutely stellar crew lined up for tonight. We have several of our students presenting a wonderful show on stars. So give it up digitally for Guggen, Noah, Jean-Luigi, Sana, and Palvisha. Take it away.
Hello everyone, I'm Guggen and I'm here today with Jean-Luigi, Noah, Palvisha, and Sana from the Alan I. Carswell Observatory at York University to talk to you about stars. Stars are everywhere. The Milky Way alone contains hundreds of billions of stars, one of them being our sun. And when you look up at the night sky, all the stars you see are a part of our home galaxy. With billions of galaxies in the observable universe, the number of stars in the universe seems too great to imagine. But what exactly are stars? A star is essentially a hot ball of plasma or ionized gas that continuously emits light. They are composed primarily of hydrogen and helium, and their energy comes from nuclear fusion at their core. Nuclear fusion is a process where atomic nuclei combine to create another larger atomic nucleus, and in stars, the common reaction pathway is the fusion of two hydrogen atoms to yield a helium atom. Stars emit massive amounts of energy every second, which sets them apart from other objects in space, and they are very hot, with temperatures reaching tens of thousands of degrees Kelvin. They are relatively stable in size, and this is because they are at hydrostatic equilibrium. This means that the outward force of the gas pressure inside matches the gravitational force pushing inwards. Star structure can vary depending on the type of star, so we'll be focusing on the sun for now. There are three main inner structural elements of the sun and most stars. At the center of the sun is the core. This is where most of the nuclear fusion activity occurs, and it is the hottest part of the star, with a temperature of 10 million degrees Kelvin. As some higher mass stars age and heavier elements are burned, they build up in the core and the nuclear burning region is pushed outwards around the heavier elements, as shown in the image on the bottom left. Next is the radiative zone. This is a layer around the core of the sun where energy or heat from the core is transported outwards via electromagnetic radiation or thermal conduction. It is cooler and less dense than the core. Lastly, the convective zone around is the region above the radiative zone where energy is transported outwards through flowing convection currents. In total, energy travels from the core of the star outwards through the radiative zone and the convection zone until it reaches the sun's surface. The convection zone is the coolest part of a star's interior. The image on the top right shows the transportation of energy through the star's main inner layers, from the core to the convection zone. The sun also has an atmosphere with three main layers. The innermost layer of the atmosphere is the photosphere. This is the layer where energy from the sun is released as light. It is therefore the visible surface of the sun. Sunspots, which are cooler and darker parts of the surface of the sun, are on the photosphere. The next part of the sun's atmosphere is the chromosphere. It is less dense than the photosphere and appears only during total solar eclipses as a dim red glow, such as in the image on the bottom left. It cannot normally be seen because the photosphere underneath is so much brighter. Both the photosphere and the chromosphere range in temperature from approximately 3,000 to 7,000 degrees Kelvin. The outermost layer of the sun's atmosphere is called the corona. This layer extends millions of kilometers into space around the sun and has no outer limit, but it is vastly less dense than the photosphere and chromosphere and is only visible with the naked eye during a solar eclipse. Despite its distance from the core and its lack of density, temperatures in the corona can reach millions of degrees Kelvin. In the images below of the sun during a solar eclipse, the corona can be seen as the plumes of gas extending outwards. Now that we know the basics of what stars are, let's move on to how we characterize them. When we research stars, there are a bunch of different parameters that we measure, such as mass, temperature, and luminosity. Mass and luminosity are two of the most important parameters in star research, and we use these to classify them, which you'll learn more about later on. Since the sun is the closest star to us, and therefore the one that we know most about, our measurements of other stars are also compared to the sun or measured in terms of the sun. One solar mass, which is the mass of the sun, is a standard astronomical unit of mass. It is equal to approximately 2 times 10 to the power of 30 kilograms and is denoted as m solar. The circle with a dot in the middle is the symbol for solar. Masses of other stars are written in terms of solar masses. For example, the star Betelgeuse, which can be seen as the bright red star in the top left corner of the constellation Orion, is 11 solar masses. Luminosity is another main parameter for stellar research and refers to the total amount of electromagnetic energy or light emitted per unit of time by a star. One solar luminosity, denoted as L solar, is equal to 3.83 times 10 to the power of 28 watts. The star Sirius, the blue star on the bottom right, is the brightest star in the night sky and has a luminosity of about 25 solar luminosities. We use these symbols pretty often to denote measurements for other stars. Another point of research for stars is composition. Chemical composition of a star can help us determine its age, and we use spectroscopy to find a star's composition. Different elements yield different spectral lines, and so a star's emission and absorption spectra can show us which elements it is composed of. Pictured on the lower left is the spectra for our sun. Helvetia is up next to show you how we classify stars.
So now that we know what a star is and how stars work, we can talk about their classifications. In order to do that, it is important to understand what an HR diagram is and how it works, since HR diagrams use the properties of stars to classify them. Looking at this HR diagram, you'll notice luminosity on the left and temperature or the spectral class on the bottom. HR diagrams can also be plotted with absolute magnitude versus the color index and yield the same result. This is because these properties are all related. The absolute magnitude is a measure of luminosity, just a different scale, and the temperature or spectral class are related to the color index. The hotter a star is, the bluer it is in spectral class, and the lower its color index. Whereas, the cooler a star is, the redder its spectral class, and the higher its color index. The plot of the temperature or spectral class, or color index with luminosity or absolute magnitude, also arranges the stars based on their mass, as a star's mass is correlated with a temperature or a spectral class or color index. The more massive a star is, the more hydrogen it has to burn, and the hotter it is as a result, and vice versa with a lower mass star. Now that we know how stars are described on the HR diagram, we can talk about their classifications on the diagram. One of the ways the HR diagram classifies stars is through spectral types, which is one of the axes on the diagram. The spectral types are O, B, A, F, G, K, and M. O-type stars are the hottest and bluest, and M-type stars are the coolest and reddest. This classification system was first established in the 1890s when Annie Cannon joined Harvard Observatory working under Edward Pickering as part of his group. Pickering's classification system classified stars based on the strength of hydrogen lines or abundance of hydrogen. Those with the most hydrogen were labeled A, going 22 letters down to the ones with the least hydrogen. Cannon realized that the stars could be classified based on temperature instead, and developed a classification system where the 22 initial groups were watered down to just the 7 I mentioned before. She classified them from hottest to coldest, and what was interesting was that the hottest stars were O stars and coldest were A stars, so the original system was reversed. This isn't the only classification system on the diagram. There are different classes of star groups on the diagram as well. For instance, main sequence stars. We know that our sun is a star, but what is classified as is a main sequence star. A main sequence star is one that is readily burning hydrogen into helium and can be found on the main sequence, hence the name on the HR diagram. The time a star spends burning hydrogen into helium is the time it's considered alive, and also the time it spends burning hydrogen into helium is also the time it remains on the main sequence. Our sun is located about halfway through the main sequence, and this is because it's about halfway through its lifetime of burning hydrogen into helium. Once our sun exhausts its supply of hydrogen and can no longer burn hydrogen into helium, it'll move off of the main sequence and onto the red giant branch. There are also super red giants, but those arise when stars much more massive than the sun move off of the main sequence. Sana will talk about this in a bit more detail. When a star can no longer sustain itself as a red giant or super red giant, it'll move to either becoming a white dwarf or a neutron star or black hole. Black holes aren't on the HR diagram. You can also see blue supergiants on the HR diagram. These aren't part of the life cycle of a star. They're just actual stars that are just incredibly hot and incredibly massive. They die very, very quickly.
You now know that stars spend their lives on the main sequence, but what happens to stars before and after they turn into main sequence stars? All stars begin their lives in giant molecular clouds, which are the coldest and densest clouds of gas in the universe, and examples of which are shown on the top right of the slide. Stars begin to form when the cloud begins to collapse under its own weight, creating many young stellar objects. These objects will spend some time accreting gas from the surrounding cloud and contracting, and this contraction causes the gas to heat up. Eventually, the core region of the young stellar object will reach temperatures of about 10 million degrees Kelvin, causing hydrogen fusion to ignite in the core. After some more time, the star will settle into hydrostatic equilibrium, bringing the star onto the main sequence. During this process, the particles and radiation emitted from the stars will begin to sweep away and heat up the surrounding gas, causing it to light up and creating beautiful nebulae like the Orion Nebula, shown on the bottom of the screen. How about the death of stars? Stars of all masses begin their deaths in exactly the same way. However, the exact paths that they take vary wildly depending on their mass. All stars begin to evolve off the main sequence and thus die when the hydrogen in their core runs out. When hydrogen fusion in the cores of stars stops, there's no longer any radiation pressure to counteract the inward force of gravity, and thus the core of the star will begin to collapse under its own weight, which causes it to heat up. Since hydrogen fusion creates helium, stars that have just evolved off the main sequence are left with cores of helium that, just like hydrogen, is also capable of fusion at temperatures of about 100 million Kelvin. Here's where the evolution begins to differ. The lowest mass stars, called M-dwarf stars, will never be able to reach temperatures high enough to start helium fusion. This is because, just like with the birth of stars, the gravitational collapse is what's responsible for the increase in temperature. Thus, the more massive the star, the higher the core temperature will reach. Since M-dwarfs are so small, they lack the necessary mass to cause helium fusion, and will thus evolve directly into white dwarfs, an incredibly small, dense stellar remnant held up by the pressure that nearby particles exert on each other. White dwarfs are sometimes referred to as the hot potatoes of the universe, since all they really do is sit there and radiate away energy. It is important to note that no M-dwarf stars have ever evolved off the main sequence, since they live for trillions of years, while the universe is only about 13.8 billion years old, so they have not had enough time to die. The evolution of higher mass stars, such as the Sun, begins the same way as low mass stars, but is more complicated since they can perform helium fusion. In this case, when hydrogen fusion in the core stops, the star will contract, causing the core temperature to increase. Instead of evolving directly into a white dwarf as low mass stars will, the temperature increase will cause hydrogen in the area surrounding the core to ignite, called shell fusion. All this causes the star to get brighter and expand into a red giant star. Eventually, the core temperature of the star will be high enough to ignite helium fusion in the core, creating carbon and oxygen. Once helium in the core runs out, solar mass stars will no longer have any fusion in the core since they do not have the ability to fuse carbon and oxygen. Instead, what will happen is the helium in the surrounding area of the core will also begin to fuse, so that that star will be fusing both hydrogen and helium in shells surrounding the core, as indicated in the diagram on the left. This combination creates incredibly unstable conditions, and powerful pulses of energy driven by these two fusion shells will cause the star to literally rip itself apart. The star will finally end its life by blowing off its outer layers into space, creating a planetary nebula with a white dwarf composed of carbon and oxygen at its core. Now for high mass stars. Just like with solar mass stars, high mass stars will end up with shells of hydrogen and helium that are both fusing elements together. However, high mass stars will eventually begin to fuse the carbon and oxygen in the core, generating neon. Once the carbon and oxygen in the core has been exhausted, there will be additional shells of carbon and oxygen that will be fusing outside of the core, while eventually the neon in the core begins to fuse as well. As shown in the diagram on the left, this process will repeat, during which magnesium, silicon, and iron will be generated as well. The interior of the star will begin to resemble an onion, since it has so many different layers with different elements fusing. At this point, the star will become a supergiant. Even the most massive stars in the universe will be unable to fuse iron. So once the core becomes pure iron, the star will blow off its outer layers in an incredibly massive explosion called a supernova. If a star has a mass between 8 and 30 times the mass of the sun, it will leave behind a neutron star at the core, and even more massive stars will leave behind a black hole. An example of a massive dying star is Betelgeuse in the constellation Orion. It will go supernova sometime within the next 100,000 years, so possibly during our lifetime. A fun example of a supernova remnant is the Crab Nebula in the constellation Taurus. The supernova explosion that created the Crab Nebula was observed by Chinese astronomers in 1054 and was so bright that it could be observed with the naked eye during the day for about a month after the supernova. That's how powerful these events are. The image of the Crab Nebula on the left of the slide is an image taken by NASA's Hubble Space Telescope using optical light, and the image to the right is also of the Crab Nebula, but was taken using X-ray light by NASA's Chandra Observatory. The right image provides a wonderful view of the neutron star at the core of the nebula, and you can see the disk and jets surrounding the neutron star and how it's interacting with its environment.
Plenty of our night sky is unique, interesting, and mystifying. What are some of the interesting situations that make the universe so compelling that have fascinated humanity for millennia? Now that you know about stars, types of stars, and life cycles of stars, I'm going to delve into some interesting information about these objects that populate the universe. Did you know that around half of the stars in our galaxy, the Milky Way galaxy, are actually multiple star systems? But what exactly are these multiple star systems? Here, we're taking a look at binary star systems, some of the simplest forms of these astronomical objects. A binary star is actually a set of two stars orbiting a central gravitational point. To the naked eye from Earth, though, most binary stars actually appear as a single star. We can detect them through telescopic viewing, through spectra, or through eclipsing variable stars, which is when one star of the binary system eclipses or passes over the other star, varying the brightness that can be seen of the eclipsed star from Earth. Now, be sure not to confuse binary stars with double stars, or two stars that are visually close together. It's a predicament where binary stars are double stars, but not all double stars are binary stars. As can be seen on the slide here, a great example of a binary star system is Albireo. It consists of the yellow Albireo A and the blue Albireo B. Fun fact, although they orbit a central gravitational point, they're actually 380 light years apart. If you look close enough though, what's really interesting about Albireo is that Albireo A is actually a double star itself. So although Albireo may appear as a single star to the naked eye, in actuality, it's three. Now, I just described binary stars, but as I mentioned, those are some of the simplest multiple star systems. There could be many more than just two stars in a system. An example of such multiple star systems is AR Cassiopeae, a 7-star system. Various combinations of stars in a system can also occur. It's not necessarily only two normal or main sequence stars. For example, there could be a normal star and a white dwarf, or two neutron stars in the system. The first white dwarf was actually discovered because it's in a binary system, a system with the brightest star in our night sky, Sirius, as is in the top left image. While Sirius A is a normal star, Sirius B is a white dwarf, the tiny star in the bottom left. The image on the top right, meanwhile, is a depiction of the binary star system of the two white dwarfs. Not only that, but exoplanets, planets that orbit a star other than our sun, can actually orbit stars within a multiple star system. They can orbit one star in satellite-type orbit or multiple. If they orbit two stars, it's called planet-type orbit, where the exoplanets are known as circumbinary planets. This can be seen in the bottom illustration. Another very interesting category of stars is that of variable stars. Some of the primary objects we research at the Alan I. Carswell Observatory are variable stars. These are pulsating stars, or stars that vary in brightness. There are a vast variety of ways this fluctuation can occur. The star could be eclipsed, causing the light of the star as seen from Earth to be blocked by another, for example, from a multiple star system, as I mentioned earlier. The image on the bottom is an illustration of Algol, an eclipsing variable star, and its light curve. The star could also be pulsating at the end of its life cycle, or it could be explosive. Both pulsating and explosive methods occur when the energy emitted varies over time due to competition between gravity pulling into the core of the star and expulsive forces pushing out. Variable stars, interestingly enough, can actually be used to measure and indicate distances in the universe. Edwin Hubble used variable stars to determine that there are other galaxies beyond the Milky Way galaxy. He realized that the distance to the variable star, now known as Hubble variable number 1 or V1, as is seen in the top image, is way beyond the known boundaries of our galaxy. V1 is part of the Andromeda galaxy. Because of this discovery, billions of galaxies are now known beyond our own. Thus, the study of variable stars is, and has been, crucial to understanding the universe. Another interesting thing is how stars perpetuate the formation of stars in a never-ending cycle. When stars go supernova, a remnant of which you can see in the left image, high-pressure areas are created, causing clouds to collapse and cool and forming molecular clouds, or stellar nurseries, depicted in the center image. This enables stars to form, from which partially ionized areas are left which cool and neutralize. These clouds are then blown away while the stars complete their life cycle, eventually going supernova and repeating the process. The right image shows stars in our galaxy at various stages of their life cycles. One last thing I wanted to highlight is the presence of Goldilocks stars. When looking for habitable planets in the universe, not only do the planets have to be considered, but the stars as well. The star or stars around which planets orbit must have quote-unquote just right qualities for organic life, including radiation, temperature, and the length of time the star burns for. These recommended stars are orange dwarfs, also known as K-dwarfs or K-type main sequence stars, as you can see in the middle row of the diagram. These stars are similar to our sun, but are cooler and have longer lifespans. In fact, there are 3 times as many orange dwarfs as there are stars like our sun, increasing the potential for life elsewhere in the universe. And finally, some other extremely interesting celestial objects will be explained to you by John Luigi.
All right, so star clusters are spectacular celestial objects to take image of, but also an essential study to gather more information about the life of stars. As I dive into this topic, please just try to admire that most of these pictures have been taken with either our 40 or 1-meter telescope from our staff at the Allen I. Carswell Observatory at York University during these years. First of all, what is a star cluster? Well, star clusters are a group of thousands of stars which were born from the same molecular gas cloud. Hence, stars in each cluster have approximately the same age, chemical, and physical composition. They are primarily divided into categories, globular and open star clusters. By simply looking at this image of the two, as you can see M15 on the on the left, it's a globular clusters. And as you can tell, those are much more dense at the center and close to each other, giving them a globular shape. Hence, they have a stronger gravitational bound between each other compared to open cluster where stars are much further apart, as you can tell in the image on the right. In fact, in open star clusters, the gravitational attraction is way more loose, and oftentimes they get disrupted by the encounter of other clusters or gas clouds. For instance, the well-known open star cluster, the Pleiades, one of the only few clusters to be observable with naked eye from Earth, is predicted that its stars will diverge due to interaction with its galactic neighborhood in about 250 millions of years. But now, how do actually star clusters form? As mentioned before, all stars in a cluster form from a cold dense cloud of gas and dust due to a disruption, such as shock waves from a nearby supernova or after collision with another cloud. This will trigger a collapse and initiate the birth of star formation. In the case of open clusters, as hottest and most massive stars form, they will steadily ionize the surrounding gas, forming H2 regions in the area. Due to stellar winds and radiation pressure, the hot ionized gas gets pushed away, a process that usually takes about a few million years, clearing the gas around and ending any further star formation. Unfortunately, during this gas expulsion, many young stars will get lost unless they're strongly gravitationally bound to each other. In fact, only 30% of the gas in the cloud core form stars that will remain bound together. Since most stars get pushed away, open star clusters are dominated by hot blue young stars, making the life of these clusters very short. An interesting fact about open star clusters formation is that sometimes two clusters can be born from the same gas cloud, forming a binary cluster. A primary example is the double clusters of NGC 869 and 884. However, when it comes to globular clusters, astronomers are more uncertain how they're formed. It is confirmed that by observation, their stars have approximately the same age, chemical and physical composition, but possibly formed by multiple generations of gas clouds over millions of years. However, during this formation, each globular clusters differ. They think that some globular cluster might have encountered other giant molecular clouds, triggering a second star formation. Another idea is that some of these clusters might actually merge together, showing a significant range in ages and metals in the gas. Observation also indicate the globular clusters form primarily in areas where interstellar medium has very high density than other regions. As today, no known globular clusters display active star formation, which is consistent with the view that globular clusters are typically the oldest objects in the galaxy and were among the first collections of stars to form. As mentioned before, the reason we study star clusters are because we want to understand the stellar evolution, as most variable parameters of each star in a cluster, such as the distance from Earth, material composition, are pretty much the same. Hence, the difference in their apparent brightness depends only on mass, which is very helpful. If we consider an open star cluster, once we plot all its stars in an HR diagram, we notice that most of them, they're going to lay on the main sequence, with only few massive stars evolving away from it as they become red giants. These transition areas can be helpful to estimate the age of the entire cluster. As an example, as you can see in the image of the HR diagram, we have two open star clusters displayed, NGC 188 in blue and M67 in yellow. As you can see, the stars in NGC, they have a lower turning point, which means the star in the cluster spend more time on the main sequence. Therefore, it is older than the stars in M67, which have a more massive stars that evolve faster to red giants. Furthermore, clusters are a crucial step in the measurement of incredible far celestial objects, as they're too distant to have a direct determination of their distance. To determine the distance of close open star clusters, there are two methods. The first one is star parallax, which rely on the small change in apparent position of stars as seen from Earth during the year. And the second one is called the moving cluster method, which measures the proper common motion of clusters member compared to their apparent motion across sky revealing at a vanishing point. As distances of nearby clusters are estimated, we can extend the distance scale to further ones by plotting two clusters on the HR diagram, as you can see in the image, one with known distance and the other one with unknown distance. The most distant known open cluster in our galaxy being found is Berkeley 29 at a distance of about 15,000 parsecs. Lastly, determining open star clusters distance help us calibrate the period luminosity relationship of variable stars. And lastly, before we conclude tonight's session, here are some worth mentioning star clusters. From bottom to left, we have M92, a globular clusters in the Hercules constellation, distant about 26,000 light years away from Earth. Considered one of the brighter in terms of absolute magnitude and older globular clusters in the Milky Way. In absolutely perfect weather condition, the cluster can actually be observed with naked eye in the northern hemisphere. Bottom to left, we have M11, one of the favorite among staff at the observatory. This is one of the richest and denser open star clusters located in the constellation of the Scutum, also known with it's one of the most massive clusters, as there is a mass estimation between 3,700 to 11,000 times the mass of the Sun. This cluster is also called Wild Duck, takes the name from the brightest stars forming a triangle shape resembling a flying flock of ducks. This is because early version of telescope would not have a higher resolution while observing, and hence neglecting most of the dimmer stars in the cluster, allowing astronomers to observe only the brightest one. And lastly, top to right, we have NGC 7789, which is a young star open cluster discovered by Caroline Herschler, actually one of the first women to be honored with a gold medal at the Royal Astronomical Society in 1828, and also one of the first to be named an honorary member of the Royal Astronomical Society in 1835. Like M11, this cluster is also known by another name, as the brightest stars visually form a specific pattern. Can you guess it? Comment below and we'll give you an answer during the Q&A session. All right, well, everyone, you've been listening to the Alan I. Carswell Observatory Weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Noah, Sona, Gagan, Pelvisha, and myself, John Luigi. Make sure to leave any comments in the comment section of the video. You can always connect with us on Twitter with the handle @York Observatory, and check out our website for show notes, content, updates, and content info at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.
Thank you, everyone. That has been our broadcast. And just as a reminder, we will be online to answer questions in the YouTube comments and also the video comments for about the next 20 to 30 minutes. So if you do have any questions from tonight's broadcast, feel free to ask them there.